Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olsen to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hello, everyone. Welcome back to the Rare Earth Exchanges podcast. Today, you're joined by me and my co-host, Daniel, and we are joined with two people from the Idaho National Laboratory, Bob Fox and Travis McLing. They are, I want to say, veterans in this space, in the rare earth space. I'm really excited. We're practically neighbors. Daniel and I are here in Utah. You guys are up in Idaho. And I love this area so much. So Bob Fox, Travis McLing, welcome to the show. We're really excited to have you here. Bob, you are the advanced problem solver in the processing arena of rare earths. And Travis, you are the chief geologist. Did I get that right?
That's correct. I work on the upstream side. I provide the rocks and minerals to Bob Fox's team to get the metals into a usable state.
That's awesome. And I'm honestly really excited about this conversation because of that dynamic that you guys have of getting it from the ground and making it also usable later on. So first question I've got for you guys is, when most people hear about rare earths, they picture either rocks in the ground, Travis, or magnets at the other end. From where you guys sit, your perspective, what is the most misunderstood part of the rare earth story?
The most misunderstood part from my perspective is that the need and how the supply chain and the lack thereof impacts people on a day-to-day basis. Every single thing we do in a modern technology-based economy is based on the very metals that we're talking about here. And we're not just talking about rare earths, but we're talking about the whole suite of the 60 elements in which we're underwater in supplying. That's not a technical answer, but I think until the social license gets to a point where people understand that we are sourcing these materials from unstable or adversarial nations almost entirely, that I think that's the biggest single point for me is our folks in the country need to understand that part of and how important those metals are. And let's face it, no matter what you do, there's a hole in the ground somewhere that those metals came out of.
Yeah, we agree. We talk about that a lot here. Bob, what are your thoughts?
So, Dustin, thank you. I would add that what seems to be misunderstood the most by folks is when they hear rare earths is that they're not rare. They're certainly not in as large abundance as, say, sodium or aluminum, but they're not rare. Rare earths do appear in the Earth's crust, and we have known ores that contain rare earths, and we know how to mine those, resource those, and to recover the rare earths from those minerals. So they're not rare. They're known and they are recoverable. But they're also not incredibly high value. They're not as high value as your coinage metals or platinum or gold. So the economics tied to rare earths is incomparable to the economics applied to gold resourcing or platinum resourcing. So there are economic considerations there. They are critical, meaning critical as in a supply chain pinch point can occur. There are supply chains that supply rare earths, and those supply chains are disruptible. And especially you see disruption when you start to have one particular country or one particular source being the only source or being the major source. So no, they're not rare, but when you have one source dominating, then that particular source can manipulate the market, can manipulate supply chains, and therefore make it very hard for you to get this critical material that is needed for your technology. Okay, so the other thing that I think that people need to understand that is a misperception is these things are used in technology, exactly like Travis said. They are used in technology. They are used in advanced technology, not only for electricity generation, but they're also used for defense of the nation and defense platforms. So many things that are misunderstood about rare earths, and I just went through a few of those.
That's a great emphasis.
I'll, I'll add something here real quick, just what Bob said, and leave it to the chemist to give the geology answer. I love that. It's a function of how closely we work together. But Bob did indicate that they are not rare. They occur in the crust at about the same concentration as copper. And I always say in my presentations that I give where I'm asked to speak is that they are critical. They are not valuable. And we can talk more about that at some point if you'd like. But the processes, the geologic processes that concentrate rare earths into an area where they can be mined efficiently, those processes are rare. They don't happen as frequently as, say, copper deposits. And so in the globe, there are really only two supergiants in terms of the deposits: Bayan-Obo in China and Mountain Pass in the U.S. And interestingly, they are light enriched, meaning the lanthanides, which are the rare earths. They're the light enriched systems, and they don't have as many of the heavy, like the neodymium and praseodymium, that are so important to our magnet industry and into the energy sector. So I think it's important to know that there's a whole bunch of rare earths. Not all of them are in equal abundance, and most of our supergiants that are concentrated in high enough element concentration are high enough that you can mine them really efficiently are really enriched in the stuff that doesn't have much value at all. It's the high value heavies that are the more problematic and difficult to get at. So that gets a little more technical, and I don't often dive into that. But Bob, I wanted to make sure we laid the geologic framework for it.
I think that's important. Thank you, Travis. I think it's important to look, because there's a lot of confusion out there, okay? And we're seeing that it could very well be in a few years, maybe there could be a glut of light rare earth elements and still no heavy rare earth access. And we got a big problem, big problem. So could we talk a little bit a lot of different types of people will be hearing this and watching it, investors to policy people to, the more scientific, but what are the differences between the heavy rare earth elements and the light rare earth elements? And why do these magnets, even if it's a small amount, need these heavy rare earth inputs? And how did we become so dependent on even one? If you look at our rankings, Myanmar has a disproportionate, the Myanmar rebel situation. The whole world's dependent on this pretty much. So can we get from both of you a delineation of the difference and how some of these forces unfolded, just to educate people?
Okay. So when you resource rare earths, a lot of people don't understand that you take a shovel full of an ore that contains rare earths, you get all of them. Okay. You don't just get one. Surprise, you get all of them. Okay. And so if you went through all of the effort to get permitted and to take that shovel full of rare earth, then you get all of them. And there's a geologic distribution depending on which ore body you're talking about, at which location in the earth, and geologic, event that gave rise to that particular formation. Your ore could contain more lights than heavies, or your ore could contain more heavies than lights, or some smattering of in between. So I'll let Travis, explain more about that, but we'll just take Mountain Pass by way of example. Mountain Pass has a higher concentration of the light rare earths in the shovelful that you just took. So that means you're getting more cerium and lanthanum than you are anything else. So why is that important? It's important because if your product is a neodymium iron boron magnet and you want to have that magnet perform in high temperature applications like in electric vehicle motors, etc., then you need some amount of terbium or dysprosium, or terbium and dysprosium, in your neodymium, praseodymium formulation for your magnet. So in your one shovelful, the majority of the atoms are going to be cerium and lanthanum. You have got to get all of those lower economic value and lower technological value materials out of the way so that you can isolate your neodymium, praseodymium, terbium, dysprosium so that you can make your magnets. Getting all those other things out of the way costs money, costs time. There's a cast the background. Travis, I'm gonna punt to you now.
Yeah, I think Bob did a really good job of explaining it. The reason why these, neodymium magnets, I'll give just for an example, neodymium-based magnets, these are high field strength magnets, and they have a wide dynamic working range. That means there's a temperature range in which they work. They can work at very high temperatures and maintain their full strength. And so they're very, very good at working for a long time. If you want to fly a drone, you want a very high strength magnet that isn't very large. So when you see the explosion, no pun intended there, of drone use across the globe, you want to have those. You don't want to have magnets that weigh a lot. You want to have these little tiny magnets. And Bob's right. And these large ore body forming deposits tend to be light enriched. And so if you want to Google, whoever's folks are listening, want to Google rare earth enrichment, you can look at that and you can look at the trend and see why most of these systems are really high in cerium and really low on the neodymium side. It's just the way nature, crustal abundance happens to work. And the main ores that we use, like bastnasite, that mineral is a light rare earth enriching mineral. There are other minerals that are not. They're very high in the heavies, like monazite. But one of the problems Bob talked about was he talked about you get in one scoop you get all of them. Well, that's true, but you also get all of the bad actors that come with them. So in association with these ore bodies is thorium, and thorium can be about a weight percent in some of these deposits. And so when you scoop up and you're getting all of these elements that have very low value, and in fact we are in a low rare earth cerium kind of glut right now. We have plenty of that material that has really very low value. But you still have to remove the thorium that comes associated with that. And you still have to separate the elements that have the higher value. So ideally, one would like to be able to find an ore body that is enriched in the heavies. Problem is, those kind of deposits don't occur in these great big, highly concentrated ore bodies like Bionobo and like Mountain Pass. A lot of them occur in very small, as either placer type sands, or they occur in small dike-like features like we have here in Idaho, where you're heavy and rich, but you have small dikes that would need to be mined in a very different way. And so being able to work across the team like Bob and I do here at Idaho National Laboratory and with our collaborators is coming up with methodologies that don't require us to move the whole cubic yard, but to move the little bit that contains the high value mineral and remove that selectively. And that's where the technological challenge is right now. Currently, you get them all. If we could go to the position where we could leave all the gangue and the lower grade materials and stockpile them or backfill them, we could reduce the cost and we could increase the supply where we need that. We're starting to see more and more people. You've seen some of the companies like Energy Fuels make moves in the monazite area, and they've started to produce their very first NdPr concentrates straight out of the monazite ores. But again, they occur as a waste product from another process. And so they're the concentration. So now they have to go out across the world and look for sources for monazite sands. They're real recalcitrant and they exist at high concentrations only a few places. So that adds complexity to the whole thing. The fact that rare earths come as a they're all sisters. They all look very much like each other, and separating one from another is very difficult. It's not a flotation circuit. It's not a single pass-through refining circuit. It's hard. And so that's why we have this problem, Daniel, is that just the abundance. And then when you go through the separation process, it goes through sequentially. And you don't.
So no, that's very helpful, Travis. On that topic, and I want to talk about the National Lab in Idaho and the criticality of what you all do there. Okay. We believe that, the research has to be extremely prioritized, and that's upstream, midstream, and downstream. And I'll go into why we think downstream because of what we chronicle over in China. But if you look at upstream and the separation process and the lab's efforts, could you share with the audience some of the things that you're working on? And obviously, if they're confidential and proprietary, we don't want to talk about them. But at a high level, like what are some of the programs you all are doing? And if you could name, or do you work with companies? Is it with universities? Like, give us a sense of how you are trying to solve this problem. Because this is a major problem you just brought up, both Travis and Bob.
Why don't you take this one first?
Yeah. So by way of example, picking up where Travis left off, laparoscopic mining or precision mining, when you, instead of having to go and resource the entire ore body, if you can go and develop technology that only laparoscopically or surgically removes what you need, then the amount of time and money and effort spent downstream doing separations, you get a lot of improvement and efficiency. In addition, right now, current mining practices are trending more towards in situ mining, simply because of the lower environmental impact, lower environmental footprint, lower environmental impact, the ability to be more sustainable. And so we're looking at and developing those precision in situ types of methodologies that would allow for greater efficiency and retrieval of specific materials instead of digging it all up and making a big hole in the ground. So that's by way of example. With that, we're also looking at process intensification. So process intensification is if it takes you 5 steps to do something, process intensification is you develop technology to where you get it done in 2 steps instead of 5 steps. You get it done in half the time, half the resources, half the amount of money, etc. So process intensification. So what we're looking at is process intensification in the recovery and separation, pushing separations technologies closer to the ore phase and allowing for not only removal of a material from an ore, but then separation in situ, so that the only thing you're bringing back to the surface, or the only thing that you're trucking off of a mining location, is a more highly pure material. Okay? More highly pure. So the final thing I want to throw in there by way of example is, as Travis stated, oftentimes when you're resourcing materials, you're inevitably going to get something that you don't want, that is a bad actor. By way of example, thorium. There are others like cadmium, selenium, things that, yeah, they have a place and a purpose, but they can be toxic once you remove them out of their native environment in the ore where they were sequestered. So what do you do with these things? How do you mitigate any mess that they may cause by your action? So we're developing technology to mitigate the messes. We're developing technology that will take these materials, these bad actors, render them into a thermodynamically stable form, them right back into the ground from which they came, right there on the spot, so that you can mitigate. I'll give a real quick example. We were working with Jervois, and they're mining cobaltite in the cobalt belt in Idaho. And cobaltite is a cobalt arsenic ore. It's a cobalt arsenic. And so for every atom of cobalt, you're getting an atom of arsenic. So if you pull cobalt and arsenic up and you're trying to strip the arsenic away from the cobalt, because you really only want the cobalt, you don't want the arsenic. Well, what do you do with the arsenic once you get it away from the cobalt? So we developed chemistry that would allow us to electrochemically combine the arsenic that we strip from the cobalt, combine it with ubiquitous iron that happens to be in the ore and everywhere else, and you make an iron arsenide material, which is called scorodite, and it's a thermodynamically stable mineral form of arsenic. And that scorodite you can just bury right back into the ground because it's a stable mineral form. It ties up the arsenic. So that's by way of example, technologies that we're developing and working on, and some of the problem solving that goes into how are you doing these things? Because right now many of the problems are not being solved. They're just, the problems are thrown away in the tailings pile for someone else to solve the problem later.
That's right. And that's really exciting. People need to know about that. And, that type of innovation is going to help us, iteratively and incrementally get into a better place. 100%. On that note, there's dealing with how do you like more precision mining, separation, and then we have the refining process, and then downstream. I'll just bring this up now. What we're seeing in China is a lot of patenting of downstream use cases in multiple industry, from defense to materials science to life science. So again, I'm doing a plug. You don't even ask for it. The Idaho National Lab, we've got to fund these research labs like they've never been funded before, because we have an adversarial situation, and we just gave it away to them, by the way. I mean, I don't really blame them. We just sort of fell asleep. Travis, what's your, when you look at the support of labs and lab industry collaboration and academia, I mean, how healthy are we in the United States right now, both Travis and Bob? Like, is this going in a good direction, or do we need to be concerned?
So I'll jump in on this one, and I'll take a little bit of a step back and address part of your last question. Is that we do business with the Department of Energy, we do business with the Department of War, and our private sector business volume is growing dramatically. We get phone calls and new contracts with private sector weekly now. And so that's becoming almost a co-equal part of our business framework, where 5 years ago, we were primarily Department of Energy with some Department of War. And so that's a big deal, is that the companies are coming out and they're seeing the opportunity that they need. But let me address your question right there. I think, and this is Travis speaking from the optics of 35 years of working in a national lab kind of ecosystem, is there's reason for concern and there's reason for optimism. Bipartisan viewpoint that we have to do something to address this woeful lack of internal capacity in our country. While each side of the aisle has a different way to get there, there's a recognition that we do that. But this, if there has been in our past great examples of solving really difficult problems in a short period of time, we're talking about the Manhattan Project, we're talking about the moonshot, and others that we're currently in the AI side of things, is the critical strategic minerals part of this needs to have an approach very similar to that. We have not been producing the engineers, the geologists, the scientists of a whole variety of types to address our problem. We are short that kind of capability. I really think this is a time and a call for a focused approach by investment at places like the National Lab and our collaborators. I'm concerned with a spreading of the peanut butter approach, which is everybody gets a little bit of the resources and tries to solve it in the quiet of their office, where we need to bring together the big think tanks of people and capabilities and move these things rapidly. It's pretty clear that I'll give a talk a lot, and first thing I'll say when I give a talk is I'll stand up and I'll say the problem's economic. If there was a dollar to be made, we'd be mining them right now. Thank you very much, and I'll go sit down. And then I'll get back up and I'll give the rest of my talk, because it really is an economic problem that we face in the country. And if we produce materials at the same cost as what the Shanghai market is selling them for, China and our adversaries will simply lower the price to a point. You've seen it in lithium right now. You've seen it in cobalt. Name the metal, you'll see gallium, gadolinium, germanium. You'll see that they just keep the price suppressed and drive people out of the market. Our cobalt mine in Idaho is not open. In fact, it just went into care and maintenance now, with no intentions to open back up anytime soon, because the price has been suppressed for 5 years. So we need to do it better. We need to do it faster, and we need to have a focused approach. And I think I see indications that the federal government is getting more and more in tune with that. And also, I think that if we try to bring all 60 critical minerals across the finish line at the same time, is a losing proposition. Let's figure out how we solve 80% of the problem and get that solved. And then some of the other ones, what are the most important metals, the most disruptive metals that impact us in the largest possible way? Let's address those, and then we can begin working with the other ones that require much more finesse and more technology development. Like Bob talked about in situ mining. In situ mining works great if you have a soluble metal. But if you're trying to find a licks of something that can be permitted to go into the ground and selectively pull the metal of interest and come back and leave no harm behind or bring no harm to the surface, they don't exist. I can move a lot of metal with potassium cyanide. It'll never get permitted to go into the subsurface and replace mining operations. So what do we do in the absence of being able to use dangerous chemicals? We've got to come up with some lixiviants or mobilizing compounds that allow us to mine and pull those metals of interest, preferentially with the least gang or the least unwanted, to the surface, pull the metal out and reuse it so it doesn't cost us as much and it's benign. And, when you look at the uranium side of things, they use carbon dioxide and they use oxygen. Those are two pretty benign lixiviants. And it goes in the ground and it mobilizes the uranium. It comes to the surface, and that's how they do in situ mining. They use hot water for potash. What are we going to do in the metal side of things that can be permitted and that we don't end up losing our social license? So I got a little bit of a soapbox there, Dan.
But this is important.
I hope
that's very brilliant. A lot of brilliant points. And Bob, on that note, it's a little bit more high level, but you both are leaders. I've heard Travis speak. He had the best, in my opinion, presentation in that whole conference. Bob, on that note, critical mineral rare earth industrial policy. We write a lot about that in rare earth exchanges. We mean it, but different people interpret that in different ways. And so I think Travis raised some very compelling points about focus and, what is the 80% that we should focus on first? From your standpoint and the National Lab, are you part of a growing network that can come together and talk about these issues with impact, where we can, gain momentum in a way that we won't turn back? Because we don't have any choice, by the way. This isn't, it's a dire threat. People don't get it. What's your take on that, Bob, on industrial policy, on the lab's role, and, kicking it up a notch in terms of how we are successful, as opposed to get certain momentum, lose momentum, have groups go bankrupt and start over again?
Right. So first of all, everyone has to recognize that these materials are needed for technology. They're, in the 1950s, we didn't need them because we didn't have the technology that needed them. Today, now, we have the technology that needs them. So we either figure out new technology that doesn't need them, which could take, decades to figure out new technology, or we figure out how to source them domestically and source them in a way that resolves the critical market pinch points, the supply chain pinch points. So the nation's strategy right now is to back off from reliance, near sole reliance on China, and start to go to other allied nations, Canada, Australia, etc., to resource materials, but also to recognize the fact that we own our consumerism and the results of that. And so we need to also domestically produce materials and stand up a stable domestic supply chain. And so that is, the government can throw tons of money at something, but because if the government does that, there's no guarantee of success. Be an industry, because of our capitalist society and system, and our economy is based on that. It must be an industry, private industry, that comes in and stands up and stabilizes it. The government has a role, absolutely has a role in seeding that, in helping not only with science and technology and engineering, but also in policy, trade policy, in law, environmental permitting, etc. The government has a role, but it's an all of society approach to stand up and stabilize a resource stream that then is fed into a separations stream and a refining stream and into a manufacturing stream and then an end-of-life stream that allows for recycle, recovery, circularity of the metal economy. And so the national labs play a role in that. The national labs play a role in that we de-risk technology. So we make technology and the risks related to technology more palatable to industry. We are not only inventors and innovators ourselves, but we take technologies that have been derived from academia, innovations that have been derived from industry. We take all of those and we help to de-risk those, to advance those, to do process intensification, to build in efficacy and energy efficiency so that the technologies are functioning at their greatest. So the national lab and the government and private industry and academia all have a role. It's all hands on deck. This is solving the critical material problem is essentially the Manhattan Project of our generation. It is something that is so important, we cannot fail at it.
That's
I think
very
that's
important.
great. I have a question, and maybe we can end on this one to kind of wrap up the show a little bit here. But one of the things that we hear about as we've talked to other people here on the podcast is ideas sound great, as Travis was saying, in the quiet of their office, right? Things at a small scale, the innovation is great. It looks promising, but when it comes time to really, put it to work, it breaks down. And so with that, and also a tag along question to that is scale, right? What is it going to look like to achieve this independence that we've been talking about in, say, the next 5 years? There's a lot of good things in the quiet of everyone's office that has promise, but is it actually going to come to fruition? What do you guys think?
I think you probably saw Bob and I both smile because this is a great softball. I was hoping we'd get to this question. So one of the things here at Idaho National Laboratory that we are building our core capabilities around, we do things that others can't do. So we're a nuclear laboratory, so we can work with ores that have uranium and thorium associated with them. In fact, we want to valorize the uranium, and there are folks who are looking at valorizing the thorium fuel cycle as well. But when it gets right down to it, the huge gap that exists out there, there are lots and lots of laboratories that can produce a gram of any metal that you want. The problem is, can you do it at a scale that tells you whether something's going to break? And that's what we're doing here. And we'll kick off our first project in March. You may have seen some press releases on that. I'll let Bob talk about that. But we are an engineering laboratory. We build and break things. So what we do is we're building a test and piloting facility here at Idaho National Laboratory. Like I say, our first one will be here in the spring of the year, and we're working long hours to make sure that lands here. But it takes things where you can run a metric ton to 5 metric tons per day for 5 to 6 months, and you run it every day. You look at your recovery. You look at, in the case of antimony, are you breaking the stibnite crystal, which you need for the firing of those primers? We look at that. We refine the process. We change it the next day. And we're going to run a metric ton to 5 metric tons a day for 5 months, 6 months, 7 months. And we'll have that equipment here on site. And that's something people are flocking to the lab to test, because there isn't a test facility anywhere out there that does this. And we have the space, and we have the capability and the work controls on hand, and we have the technical capability to do that, where we can work with our nearest neighbors, like the project, we work with Idaho State or University of Utah or Colorado School of Mines or Montana Tech. We can develop these piloting facilities that allow people to come and basically break their process, fix it, refine it, break their process until it gets to a point where it's durable. They can then bring the capital in necessary to develop their resource, and then downstream. Because I'm telling you, if we mine our material and continue to send it off site, off the country, we export the vast majority of our metals to Asia for refining. That just means we don't lose the game in the first quarter. We lose it in the fourth quarter, but we still lose. So we have to come to terms that we need the full supply chain. And that means that we have to demonstrate that we can provide it, and that we have to have that nascent capability downstream on the refining and the metallization side, or the final product side all connected together. Just mining it, we bear all the environmental consequences, and we ship off the raw product for upgrading the value, and then we pay a high price to return it back to the country. Absolutely unacceptable. So I'll turn over the rest of my diatribe to Bob.
So you talked about the important point being, does it scale? And ideas are great. Mature ideas that have been reduced to practice in the lab are great, but do they scale? And that is one of the fortes of the National Laboratory, is to de-risk, verify, and validate the technologies. And to make sure that they're functioning at scale, optimize them so that they do exactly what they're advertised to do. They're robust, they don't break anymore, and the economics have been worked out. So running things at a pilot scale, like the 1 to 5 metric ton per day, and doing that for a long period of time to where you get process economics and you get process behavior and you understand why it works, how it works, and you're even now projecting ahead to how to make it better, faster, and less expensive. Um, that is an area in critical material separations and technology demonstration that has languished in the nation forever, for a number of years, back into the 70s. We don't have those locations to do these pilot scale demonstrations. We're standing up a pilot scale demonstration right now in collaboration with Perpetua, and we're looking at their stibnite ore and generating the antimony trisulfide concentrate from that. So that was just announced in the news. So Idaho National Laboratory is stepping up. We have the skills, capabilities, and history. It's in our DNA to do this type of pilot scale work in response of the needs of the nation.
That's awesome. And you guys, this has been such a wealth of education and knowledge. And Daniel and I both appreciate you both for being here and willing to share your perspective on what we're seeing here in the United States. And if I could just say thanks for giving everyone the confidence to move forward through all of your efforts, through the testing, the studying, the de-risking of technology, so that hopefully everyone is more comfortable in scaling to the levels that we need to be self-sustainable. Any final thoughts, Daniel, as we sign off here?
No, I would just say, I think, Bob, I really appreciated how you articulated, our system. We have our system, and we have to bring the pieces together to, transcend this current reality. And I think, thank you both for being leaders in this space. I mean, we're dedicated to help accelerate this process. So we might be a little intense at times about it, but I think it's needed, right? It's merited right now. So we thank you both, and we would love to, come up there at some point. We'll get a tour. We'll make sure that we continue to cover what's going on at the Idaho labs and hear about some of the exciting pilots that are demonstrating scalability.
We always say that the lab is open for business. We really enjoy having you guys up, and we could easily do another 6 of these types of sessions right here that we did, because we just really scratched the surface, barely scratched the surface on some of the challenges, issues, and opportunities that are going on in critical materials. It is a great time to be a research scientist in the critical material space. It is fascinating, challenging, very rewarding, and something that the nation absolutely needs.
Yeah, and we're grateful for organizations like yourselves and others that help us get the message out, because me standing on my desk and talking about my virtues and the great team that I have, really, it's hard to get that message out into the public. And what you do by providing a mechanism for people to learn from us and from others it cannot be underestimated. A lot of times policymakers get tired of hearing scientists talk about how great we are. We really need to have that folks like Rare Earth Exchange talk about the need and the science capability that we have. We have it. We can solve this problem.
Absolutely. You guys, thank you so much. And we would love to have you again on the show to dive deeper into some of these areas, because I think the education is half the battle in just letting people know what it is truly all about. So
let us know. We'll take you up to some of these ore deposits and let you actually see them and touch them.
That'd be great. Cool. Thank you guys.
Grateful. Thank you.